Hi everyone. So in today's video, we're going to continue to talk about antiderivatives. So this is going to be our last video of new content. There's not going to be any video on Friday, and then there will be a review next week. So we're going to continue talking about antiderivatives. Specifically, we're going to fill out this table that I asked you to do on the worksheet from yesterday that has some of the most common antiderivatives. And then we'll do a few other examples, and we'll also talk about some applications of antiderivatives specifically related to position, velocity, and acceleration functions. So basically we talked about some of these in yesterday's video, but these are just some of the most common antiderivatives that are good ones to know. So I would recommend, if you haven't already, pausing the video and trying to fill out this table yourself. Just because I think these are ones that you can definitely figure out on your own and that are good ones to know. So this first one we did in yesterday's video, right? We already figured out the antiderivative of x to the n. So we figured out that the new exponent has to be n plus 1. And then in order to counteract that new exponent, we need to put the reciprocal of n plus 1 as our new coefficient. And then if we're writing the most general antiderivative, we want to tack on c. And I think I'll alternate colors because I think that'll make this maybe a little bit more legible. So in yesterday's video, we saw that in the case where n is actually equal to -1, that gives you 1 over x, right? X to the -1 is 1 over x. And if that's your function, then it actually doesn't make sense to use this kind of power rule that we wrote above. And so instead, what you want to say is, well, remember what an antiderivative is, right? An antiderivative is a function where when you take the derivative, you get this. So what function gives us 1 over x? Well, ln of x. And then we have this extra thing that we add in, which is that we put an absolute value around the x, basically to guarantee that the domain of the original function and the antiderivative kind of match up. So that's our antiderivative for 1 over x. So what about just for n on its own? So just a number. So think about like if we had 5 or 2 or -3. So what function, when you take its derivative, do you get just a number? Well, it would be that number times x. Right? So if you take like the derivative of 3x, you get 3. If you take the derivative of 5x, you get 5, things like that. All right, what about e to the x? Well, that one is one of the easier ones, right? The antiderivative of e to the x is e to the x, because when you take the derivative of e to the x, you get e to the x. Okay, next we have a cosine of x. So what function do you need to take the derivative of in order to get cosine of x? Well, sine of x. So this next one is there's a little something extra going on here. So we have to think about what function do you need to take the derivative of in order to get sine of x. So you might initially guess cosine of x plus c. But what's the problem with that? Well, if you take the derivative of cosine, you get negative sine, and we want to find the antiderivative of just sine of x on its own without a negative sign. And so what we need to do is introduce a negative sign to the cosine, because now if you take the derivative of negative cosine, you're going to get negative sine of x. And so that will give you just sine of x. Next up, we have secant squared. So that one, we know that the derivative of tangent is secant squared. So that's where that comes from. And then these next three are ones that maybe we definitely haven't used these quite as much in this class, but they're going to be pretty important, especially I'd say this last one in Calc 2. So this first one here is the derivative of inverse sine. So the antiderivative of this would be inverse sine of x. And then the next one, when you have the negative sign out front, that is the that is the derivative of inverse cosine. So inverse cosine is the antiderivative of that expression. And then the last one here, what's the antiderivative of 1 over 1 plus x squared? Well, that is inverse tangent of x. Okay, so yeah, those are basically the ones that I would expect you to know, like on the final exam. you'll see that in 152, things will get a lot more complicated in terms of like what types of things we can take the antiderivative of, but this is our kind of starting point. So I want to look at an example now. So last time every time we wrote out an antiderivative, we always had this plus c thing, right? Because what we figured out was that just being given the original function isn't enough information for you to determine the antiderivative, right? Because you don't know what the constant was. And so today we'll see that if you just add in a little bit more information, then you actually can figure out what the constant is. So in yesterday's video, we focused on finding general antiderivatives. And so what do I mean by that? I mean basically the plus c thing, meaning, what's the most general antiderivative? It's always going to include plus c. So for example, we said that if you're taking the very first example we gave was if your original function is 2x, its most general antiderivative is capital F of x is equal to x squared plus c. So how did we kind of visualize that? Well, if you look at the graph, so here I graphed x squared plus c. So I just put in like a slider for c. And basically what we talked about is that it could be any of these, right? It could be a parabola that lives anywhere moving up and down because all of those parabolas have the same derivative. But looking at this picture, we can see that if we knew a little bit more information, like let's say we knew one point that this graph went through, as soon as we knew one point that it went through, that would be enough to like pin it down and say, oh, okay, it's this one, right? It's not some other one, it's this one. And so that's what we'll be doing in this next example. So today, we'll see that if you're given a little more information, you can find a specific antiderivative. So let's do another example kind of similar to one that I just wrote, excuse me, that I just wrote above. So I'm going to rewrite basically the same function. So if f of x is equal to 2x, or sorry, f of x is equal to 2x, and f, so capital F, its antiderivative, let's say that f of 1 is equal to, what did I say here? I think 10. Actually, let's say 12. Find the antiderivative f of x. So basically here we're going to start by finding the most general antiderivative, but then because we have this extra piece of information, that will allow us to figure out specifically what the exact function is that is our antiderivative. So the general antiderivative would be, as we just wrote above, capital F of x is equal to x squared plus c. And so to find the specific one, we need to find c. Right? We need to figure out like what exactly is that number that we're adding in this specific antiderivative. So how can we find that? Well, we can plug in 1 for x and set it equal to 12 and see what that gives us for c. So if we plug in 1, we get 1 squared plus c. So that would be 1 plus c. And then the question told us that that should be equal to 12. So we're now going to set that equal to 12. And so that allows us to then solve for c. So if we subtract 1 from both sides, we get c is equal to 11. And I guess I shouldn't really box that because that's not really our final answer. So what's our final answer? Our final answer would be that the antiderivative is capital F of x is equal to x squared plus 11. So why is that the correct answer? Well, basically it hinges on two things. If we take the derivative of this, of x squared plus 11, we get 2x. So that's one of the kind of requirements. And then the other thing we need is that when you plug 1 into this function, you get 12, and that is the case here. So that is why this is the specific antiderivative satisfying that property. So I want to do another example kind of along those same lines. So let's say we're going to find, let me actually say it this way. So let's say that if lowercase f of x is equal to 2e to the x minus 3x squared plus square root of x, and f of 0 is equal to 5, let's find f of x. So the antiderivative, the specific antiderivative that not only kind of has the right properties as an antiderivative, but that also satisfies f of 0 is equal to 5. So our first step is to write down the general antiderivative. So going through term by term here and figuring out what we get for the first part just 2e to the x, right? Because the derivative of 2e to the x is 2e to the x. And then what about this next part? Well, there's kind of two different ways to do this next term here. So one thing is to just kind of recognize that if you have a 3 and an x squared, that comes from x cubed, right? Like the derivative of x cubed is 3x squared. So you could kind of just like recognize that, or you could do it the way we've been doing all the other ones. So you could also just say, okay, I'm going to pull aside this 3, and then I'm going to focus on the antiderivative of this. So that would be 2 plus 1 is 3, and then I multiply it by 1/3. And so you're going to get the same thing, right? If you multiply 3 by 1/3, it becomes 1. And then this next part here, square root of x, so that's the same as x to the 1/2. So that gives us x to the 3/2 as our new exponent. And then we take the reciprocal of 3/2 and put that as our coefficient. And then we have plus c. So let's clean this up a little bit. So this would be 2e to the x minus 1 times x cubed plus 2/3 x to the 3/2 plus c. So now we need to find f of 0. And one thing I just really want to point out, and this is like a common mistake people make, a lot of the time people will look at this and they'll just assume that that means that c is 5. That actually is not the case in every function. So in this case, that is not going to be true. C is not going to be equal to 5 because when we plug 0 into e to the x, e to the 0 is 1, not 0. So just be careful. Don't make any assumptions that, just because when you plug in 0, you get a number. That doesn't mean that c is that number. In some cases, it will be. Like if you have a polynomial, for example, then that's true. But as soon as you have something like e to the x or cosine of x or anything where when you plug in 0, you don't get 0, that rule will fall apart. So just like plug in 0 and see what you get. So if we plug in 0, we get 2 times e to the 0 minus 0 cubed plus 2/3 0 to the 3/2 plus c. So the nice thing is that anything 0 raised to any power is 0. So this whole thing just simplifies to f of 0 is equal to 2 times 1, right? E to the 0 is 1, so we just have 2 plus c. And so now we can set this equal to 5 because we know that f of 0 is supposed to be equal to 5. And so from here we can solve for c and we find that c is equal to 3. And so once we find c, then we can write down our specific antiderivative. So it's going to be 2e to the x minus x cubed plus 2/3 x to the 3/2 plus 3. So this is the function where if you take the derivative, you get what we started with, you get the function that we're looking for, and then additionally, if you plug in 0, you get 5. So it satisfies both this kind of general antiderivative requirement and then also this specific point that it's supposed to go through. Okay, so next thing I want to do, so I want to do a couple of kind of trickier examples of antiderivatives that require like a little bit of guess and check, and then we'll get into the velocity and position type questions. So maybe I'll label this. These are kind of trickier antiderivatives. And we'll see that when you get to 152, calculus 2, you'll see that there's kind of there's going to be like a more concrete way of dealing with these types of functions, but I really think that guess and check is a really good way to like get comfortable with these functions. So first example I want to do is I want to find the antiderivative of f of x is equal to e to the negative x. So we're going to do, we're going to find the most general antiderivative. We don't have any information about a specific antiderivative for this problem. So let's do guess and check. I know I feel like there's something, guessing seems like it's like a bad idea, but truly in these cases, I think guessing is one of the best ways that you can gain understanding of what's going on. So personally, if I had to guess on this, I would think, okay, well, I know how e to the x works, right? The derivative of e to the x is e to the x. So I might guess f of x is equal to e to the negative x plus c. So let's check that. And how can you check these questions? Well, you can just take the derivative. And if you take the derivative, that should give you your original function. So if we take the derivative of this, we get e to the negative x. But then because the exponent is not just x, it's negative x, we have to use the chain rule, right? We're going to have to use the chain rule for this part. So we have to multiply this by -1. And so we actually end up with negative e to the negative x. And that's not what we want, right? We want just e to the negative x. So how can we kind of like compensate for that? Well, if we include a negative sign in our antiderivative, then that will cancel out with the new negative sign and it will work out. So I just put an x here, that didn't work, right? But let's try another guess. So if we guess instead negative e to the negative x plus c, let's check what happens with that. So this time we have a negative sign from the get-go, right? That just kind of comes along for the ride. And then we have e to the negative x, and then we multiply by -1 because of the chain rule. And so that comes out to be positive e to the negative x, and that is what we were looking for. And so that tells us that this is our correct answer. So let's do another one kind of along the same lines. So this time we're going to find the antiderivative of g of x is equal to cosine of 3x. So again, I would recommend guess and check here. So let's make our first kind of educated guess. So personally, I look at this and I would probably guess, I know that the antiderivative of cosine of x is sine of x. So if it was just cosine of x, then we would know, okay, yeah, that means the antiderivative is sine of x plus c. So I might guess sine of 3x. But let's actually check that and see if it works. So if you take the derivative of sine of 3x, that would require that you first say, okay, cosine of 3x, that's kind of the outside part of the derivative, but then you have to multiply by the inside derivative. And what's the inside derivative in this case? It's 3. So this would actually give us 3 times cosine of 3x, and that's not what we want. We want our derivative to just be cosine of 3x. So this is kind of like with the power rule, right? With the power rule, you have to have this kind of compensation going on. We're going to do the same thing here. So how can we compensate for this 3? Well, if we put a 1/3 in front of our function, so if instead we guess 1/3 times sine of 3x plus c, now when we take the derivative, we get 1/3 times cosine of 3x, then we apply the chain rule and we multiply by 3, and all of that is going to combine to give us just cosine of 3x. So in cases like this, you can kind of, it's this idea of like compensating, like you're kind of seeing what is the extra stuff that's going on in this problem, and how can I kind of take care of that by introducing something else to the problem. Okay, so one last thing for today is going to be now talking about, like I said, kind of an application of antiderivatives to physics, really. So yesterday we talked about how, in general, if you have a function f of x and you take the derivative, you get f prime of x, right? So we said going this way, this is taking the derivative. And that means that if you go the other way, that's taking the antiderivative. And then if you have if you take the antiderivative of little f, that's where we introduce this big F. So we can basically use the same idea to figure out kind of like a relationship between velocity, acceleration, and position. So this is kind of our general picture, and I'm actually going to copy this so we can just make a little change to it in a second. So this is kind of our general, this is like in general for any function f of x. But if we're talking about the point of view of like physics, of talking about the motion of an object, so if we replace the first function here with s of t, where that represents your position function. Actually, maybe let me just write the word. I'm just going to write position. So if you take the derivative of a position function, you get a velocity function. And then if you take the derivative of a velocity function, you get an acceleration function. So basically what this means is that the derivative, we already knew, right, that the derivative of position is velocity and the derivative of velocity is acceleration, but now we also have this new way of framing that relationship, which is that the antiderivative of acceleration is velocity and the antiderivative of velocity is position. So maybe I'll just say in physics here. So this is a really kind of powerful way of understanding the relationship between these functions, because what it allows you to do is, if you only know the acceleration of an object, you can still figure out what its velocity is and what its position is. And the more information you have, the more kind of specific you can get. But even just knowing the acceleration function is enough to at least give you an idea of what the velocity and position functions will look like. So I want to do an example kind of along those lines. So one piece of information that you may be aware of if you've taken any kind of a physics class is that on planet Earth, the acceleration due to gravity is negative 9.8 meters per second. So let me just write that down. So on Earth, so what does that really mean? So the acceleration due to gravity is And I'm going to write it as a negative number. So basically, why am I saying negative? Because generally when we're talking about the height of an object, we're measuring upward as our positive direction, right? If you're like, say you're doing a problem and there's like a parabola that represents the height of a ball over time. It goes, when the ball is going upward, it's moving in the positive direction. And so gravity is counteracting that, right? Gravity is pulling things towards the earth. And so that's why we're using a negative sign on it, because it's, remember, like the relationship between acceleration and velocity, it really has to do with what's positive and what's negative. So because the acceleration is in the opposite direction as the velocity when you're throwing something upward, that's kind of why that object will start to slow down, is because of this kind of battle between the negative and positive directions. So if you throw an object up in the air, that is like this negative 9.8 meters per second squared is basically, if we kind of simplify things anyway, that's going to be the acceleration of your object. So let me kind of write that down. So basically we're going to say, suppose you throw a ball into the air with an initial velocity of 4 meters per second. And so the first thing we're going to find is we're going to find a function that gives the velocity of the ball after t seconds. So the way that we're going to come up with this is we're basically going to use the fact that the acceleration due to gravity, that's going to be our acceleration function. We're assuming that there's no other acceleration going on in this kind of system, in this problem. So we can say that the acceleration function is a of t, and maybe I'll switch colors here to show that now this is where we're starting the work. So our acceleration function is a of t is equal to negative 9.8. So it's a constant acceleration. The acceleration due to gravity of the Earth is always negative 9.8 meters per second squared. So how do we find the velocity function? Well, we take the antiderivative of, or sorry, I don't know if I said the right thing. What I meant to say is the velocity, to find the velocity function, we need to take the antiderivative of the acceleration function. So we're going to take the antiderivative of a of t to find v of t, because of basically what we outlined up here. So what will the antiderivative look like? Well, we know that when you have a constant and you take the antiderivative of that, you basically just tack on the variable to it. So how do you get negative 9.8 as a derivative? That would come from negative 9.8 times t. So we also need to add on this plus c. So how do we figure out what c is? Well, there's a little bit of extra information given to us here, which is that the initial velocity is 4 meters per second. So what does that mean? That means that when the time is equal to 0, the velocity is 4 seconds. So this means when, or actually I'll just say it this way. This basically means that v of 0 is equal to 4, right? Because initial means starting, and that means that time is equal to 0. So in this case, it actually will just be that c is equal to 4, but let's really just double check that we see where that comes from. So if we were to plug 0 into this function, we would get 0 plus c. And then we're setting that equal to 4, and so that tells us that c is equal to 4. So our velocity function is v of t is equal to negative 9.8 t plus 4. So now let's come up with the position function. So now that we have the velocity function, we can take the antiderivative of that to find the position function. So now we're going to find a function for the position of the ball. So position, when I say that, I really mean the height, how many feet off the ground it is after t seconds. And just, I don't know why that keeps popping up. And just like with the previous one, we're going to need one little extra tidbit of information. So in this case, we need to know that the ball is thrown from a height of 2 meters. So what do we do here? Well, we basically just take our velocity function and we take the antiderivative. So the antiderivative of v of t is going to give us s of t. And s of t is or maybe let's call it h because it's height in this case. So that will be our position function. So h of t is going to be equal to, so we need to take the antiderivative of negative 9.8 t. So that's going to be negative 9.8 times 1/2 t squared. And then we have plus 4t. And then we can say plus c again. Or if you wanted to, you could use a different letter because we already used c, but it doesn't really matter. So let's simplify this a little bit. So this would be now negative 9.8 divided by 2. That is negative 4.9. And so now if we look at this information that's given, it says the ball is thrown from a height of 2 meters. That would mean that the height after 0 seconds, right, the starting height is 2. And so if we plug in 0 to our function, we would get 0 plus 0 plus c. So this is going to be another case where c actually is just equal to that initial thing. But again, you don't want to assume that. It's basically because these functions are polynomials that happens. So we want to set this equal to 2, and that tells us that c is equal to 2. And so that means that our position function or our height function is h of t is equal to negative 4.9 t squared plus 4t plus 2. So this, like what we just did here, is actually like a legitimate physics. I mean, there's obviously some simplifications that are being made, but this is how equations for the height of a projectile and the velocity of a projectile, if you've ever seen those types of equations, that's really where these come from. So just by knowing what the acceleration is, and then just knowing a little bit of kind of initial conditions is what it's often called. So like the starting velocity and the starting height, that's enough to actually go all the way back to the position function for the ball. And in this case, without getting too detailed about what this graph looks like, we know that it's an upside down parabola, right? Because it's t squared and it's a negative, so probably looks something like that. And that's not too surprising. That is kind of the shape that we would expect to see if you're looking at the graph of a height of a ball as time goes on. All right, so that is it. I will see you all next week with some review videos, and yeah, see you then.